There we go. So today we're going to first introduce what we have for trig. There are some trig functions that we need to introduce and talk about what the radians are. Use a right triangle and unit circle and angle. So there are many ways we can apply our trig functions. So those are two ways we can do them. So first, let's introduce these trig functions. If this is the first time you see them, you're going to see them a lot for the rest of your life. So the first one we have sin. It looks like sin, but the full name is sine. But we just take out the E, so it's easier to write 3 letters there. So the sin, if we apply that to some angle, when we talk about angles, we often use this Greek letter theta instead of x. Okay, it's just people just like to use that more, so we use theta for the angles here. So the sine is a function. It's being applied to this angle theta. Okay, it's like f of x. You're not multiplying f times x. No, it's not like that. You're applying a function to x. So sine of theta, you're applying a function to theta. The sine is a specific function. Okay, so like the sin, those are not variables or anything that you're multiplying. It's just a function. So this should return some kind of number for some kind of theta. Okay, so input is theta, output is some number. Okay, and that depends. Similarly, we have cosine, cos. Cosine, again, we use an abbreviation, COS, it's just for 3 letters. And the final one is tan, a tangent. Okay. And the tangent of theta is the sine of theta over the cosine of theta. So if you want to find the tangent, it's the sine over the cosine. Okay. So those are our 3 trig functions. There are more, but those are basically irrelevant. Don't be mad if you like those other functions, if you know them. But I think those are irrelevant, so we'll go on. Radians. So oftentimes when we're doing trig, we don't use our regular way of measuring angles anymore. So we would say like this is like 30 degrees or something, and a whole circle would be 360 degrees. We're gonna do something different now. We're gonna use radians. So radians are different. Instead of having 360 degrees in a whole circle, we have 2 pi radians. That's a different way of measuring angles. So if we want 180 degrees like this, that's pi radians. That's 1/2 of 360. If we want 90 degrees, that's 1/4 of a circle. So that's pi over 2 radians. Okay, so we're going to use these more. So why do you think we use radians? Well, let's say that we have an angle measured in radians, and we have an arc here. All right, and we have a radius 1 of the circle. We call this the unit circle, it has a radius 1. The cool thing is that this length of this arc is just theta. That's the length of the arc. Right? If you think about it, if we have a whole circle, that's 2 pi radians. 2 pi is the circumference, right? So the length of this arc here, if we use radians, that is, of a unit circle, the number of radians is equal to the length of the arc. And that's really important, okay? That's just a new way we're going to use measure angles here. We're still going to do degrees. So just make sure you can convert between the two, and you can use the two. You can understand, oh, how much is like pi over 3 radians. Right, so that's like 1/6 of a circle, which means it's 360 divided by 6, 60 degrees. So that's kind of what the process you would do to convert them. So that's just a new way we're going to use these, and they're used more with trigonometric functions. So this should be relatively quick. Convert the degrees to radians and convert the radians to degrees. Okay. So I think it would be better if you found all your answers and you chatted all of them to me in one message. So that would prevent some cluttering. All right. So how do we do these? 60 degrees. What fraction of a circle is that? Well, that's 60 over 360. So a whole circle is 2 pi radians, which means we just multiply this to find how many radians we have. This goes to 1/6 pi over 3. First one's pi over 3. Next one, what fraction of a circle is 240 degrees? Divide that by 360, we get the fraction. Multiply that by 2 pi, which is the whole circle of radians. And we should get 4 pi over 3. Okay, next one. 180. Well, what fraction of a circle is that? 1/2. That should just be pi. So next one is 50 degrees. What fraction of a circle is that? 50 over 360. Multiply that by 2 pi. Let's cancel these. 118. 5 over 18 pi. And that's the last one. And then we go degrees. Radians to degrees now. So What fraction of a circle is pi radians? Well, pi over 2 pi, just multiply that by 360, 180, okay? Next one, what fraction of a circle is 7 pi over 4? Well, we just divide this by 2 pi, and we multiply this by 360. If you were to do the arithmetic, it would get you to 315. So another way you could do these, if you were to think about it, draw in this, like a coordinate plane. Let's say the angle is going to rotate around here. So what does 7 pi over 4 look like? Well, we know that 3/2 pi gets us to here. That's an extra 1/4 pi. So it gets us to somewhere like here. So we can conclude that the angle looks like this. Okay. And from graphically, we can see, oh, 45 degrees less than 360. So that's another way you could get it with a graphical method. Okay. 4/3 pi, 4 pi over 3, same thing. Okay, and this would get you to 240. Any questions? Now let's get started with the actual trigonometry. So now we've got our angles down. We're going to talk about trigonometry in a right triangle. So we have this little acronym here, SOHCAHTOA. So let's have a right triangle real quick. Any generic right triangle. And we take an angle here. Let's say this is angle theta. So the acronym tells us is that the sine of theta here, S means sine, equals O over H. So what are O and H? Well, opposite side. O equals opposite. H is hypotenuse. And we'll look at these later. A is adjacent. Okay, so when we say so, that's sine of theta is the opposite side of the right triangle over the hypotenuse. So it's going to be this side divided by this side. Okay, that's the definition of the sine. That's a function. Okay, if we plug in, I don't know what this, if you were to measure this with a protractor, it looks kind of like 30, like 25 degrees. If you were to measure that with a protractor, you would find 25 degrees. And you were to plug that into a calculator. So this is my TI-83. There's a sine button there. If you press sine and then you press 25 degrees, if you do that, it will give you the ratio of the opposite side over the hypotenuse. Okay, now let's look at cosine. What is the cosine of this angle theta? Adjacent over hypotenuse. This side, let me get rid of this stuff here. Adjacent over hypotenuse. So it's going to be this side, which is adjacent. Adjacent means next to. So this side is next to the angle over the hypotenuse. So this side over that one, we get the cosine. Okay. Tangent. The next one, the last one's tangent, right? You can probably guess by now. T is tangent. Opposite over adjacent. Tangent is opposite over adjacent. So we take this side divided by this side. And that will be the tangent of our angle here, whatever it would be. Okay. Remember when I said the tangent of theta is the sine of theta over the cosine of theta? Right? So if we were to divide O over H divided by A over H, because those are the sine and cosine, you would get O over A, and that agrees with what we have there. So this is what you kind of want to remember, SOHCAHTOA. So, which means opposite over adjacent, which is the sine. Cosine is adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. SOHCAHTOA. All right. Any questions? So just a refresher, when we're talking about opposite and adjacent, we're talking about the opposite leg and the adjacent leg relative to that angle. Okay, the adjacent one is the one that's next to it. The opposite one is the one that's on the other side of the triangle. Let's find these values. Sine of angle A, cosine of angle A, tangent of angle A. And this is a 3, 4, 5 right triangle. The angle A is here. That's what it looks like. Angle B is there. I'll give you 3 minutes. Right. Sine of A, opposite over adjacent, an opposite over hypotenuse, right? So if you need to, it might benefit to write out SOHCAHTOA. Opposite over hypotenuse is 3/5. Adjacent over hypotenuse is 4/5. Opposite over adjacent, that's 3/4. Cosine of B, we're now looking at this angle now. Sine is opposite, cosine is adjacent over hypotenuse. The adjacent angle to B is this one, not this one. The adjacent side, I mean. Okay. So when we switch angles, the things are going to switch too. Now the cosine is 3/5, sine is 4/5, tangent is 4/3. Okay. This is just following what we have for SOHCAHTOA. All right. Another problem, 3 minutes. So this one should be pretty straightforward too. Sine of A in the first triangle, opposite over hypotenuse, 1/2. Triangle 2, opposite over hypotenuse, 2/4, that's still 1/2. Now we have a general 30, 60, 90 right triangle, x, 2x, and x root 3. What is the sine of A again? X over 2x, which is 1/2. I think you can see a pattern here. It's always 1/2. It's always 1/2. Which means the sine of 30 in general is 1/2. So whenever we have a right triangle, the 30 degrees here, we know that the ratio between this side, and this side must be 1/2. Right? In general, if we have a 30, 60, 90 right triangle, that's what happens, right? This is kind of like the rule for the side lengths of a 30, 60, 90 right triangle. So yes, the sine of 30, if you were to write that in your calculator right now, maybe take out your calculator if you have it. Sine of 30, it would give you 0.5. I don't know if you can see that, but it did give me 0.5. So yep, there is a definite value to every, if we plug an angle in there, there's a definite value for what that is. Okay, so if we were to use radians instead, sine of pi over 6 is 1/2. So we're going to use, if we used radians instead of degrees there, this would be also a correct statement. Okay, now this kind of branches off from the last one. Show that the value of a trigonometric function doesn't depend on what kind of right triangle you use. So this problem is trying to ask here is like, why wasn't it different when we used, for 30 degrees, we used this triangle instead of this bigger triangle? Why wasn't it different? So that's kind of like what it's asking here. Okay, so the answer here is similar triangles. So let's take this example here, sine of 20. Just some arbitrary right triangle with 20 as one of the angles, right? We could have had a much larger right triangle that looked like this. We could have had a much smaller triangle that looked like this. But the sine of 20 doesn't matter based on which one we take, the small one, the medium one, or the larger one. Why? Because these triangles are similar, right? Because why are they similar? Well, they have one angle that's the same. They all share this 20-degree angle, and they all have right angles, which means by AA similarity, they are all similar, right? The sine of 20 for all of these is O over H, opposite over hypotenuse. But for similar triangles, the ratio of corresponding sides is equal, is the same. Isn't this a ratio of sides? That means this must be a constant. And therefore, no matter what right triangle you choose, if you choose a huge right triangle or a small right triangle, the sine of 20 that you will calculate from those triangles will always be the same. That means there is a set value for what the sine of 20 is. If you see on my calculator, I just calculated that. That is 0.342. Okay, I don't know that from the top of my head, but the point of this problem was just to show you, if you plug in an angle, it's a function. There's only one output that you can have for every input. Okay? Now, this is a little difficult. Find these angles. And these are in radians because you have the pi in there. So they're not always going to tell you if it's in radians or degrees, but you can kind of assume if it has pi in it, it's going to be a radian. Okay? So find these things. Okay, so for the first one, if you're not that familiar with radians yet, it would be best to convert it first to degrees. Pi over 6 is 30 degrees. Okay. From what we've done in the last problem, it doesn't matter what kind of right triangle we use, as long as there's a 30-degree angle, it'll be good. So 30 degree. We want to find the cosine of 30 degrees, which means this side over that side. If we just use the generic form for a 30, 60, 90 right triangle, cosine of 30 is x root 3 over 2x, which is just root 3 over 2. That is the precise value of cosine pi over 6. If I were to plug that into my calculator, if you guys have a calculator at home, you should try this. How does the calculator know if I'm using radians or degrees? Right? They're completely different. How does the calculator tell? If I do pi over 6, that's still a definite value. That's like 0.5, right? Something like that, right? So how does it tell if I'm doing degrees or radians? Well, there's a button here called mode. If you're experienced with calculators, you probably know this already. You click on mode and you scroll down, there's a selection. You can choose between radians and degrees. So when you're doing these problems, make sure that when you're using your calculator, it's on the right mode. So if it's on radians mode, make sure that if you're going to plug in the degree value, it's not going to look right if you're in radians mode. So make sure that's on the right mode. If you were to calculate that, yes, it would be root 3 over 2. Cosine pi over 4. If you don't know what pi over 4 is in degrees, that's 45. 45. Triangle, 45 degrees. Any generic right triangle works as long as it has the 45-degree angle. Cosine of this angle is this bottom side over this side. Well, if this was x, then this is x root 2. So it would just be 1 over root 2, or root 2 over 2 if you were to simplify it. That's the cosine of pi over 4. Sine of pi over 6, well, pi over 6 using the same angle here, 30 degrees. Sine of pi over 6, that's x over 2x. Opposite over hypotenuse. And this is the definite value of pi over 6. Sine of pi over 4, instead of taking the adjacent of the hypotenuse, let's take the opposite of the hypotenuse. Well, the opposite is still x, right? So it's still going to be x over x root 2, 1 over root 2, and root 2 over 2. So we have this case where the sine and the cosine of pi over 4 are equal. And that's pretty interesting. And that makes sense because it's an isosceles right triangle. No matter if we choose the adjacent or the opposite, it's going to be the same value, right? So yeah, that's something to look out for. More examples here. Just right trying to find these. Okay, I want to make sure I have enough time here. So cosine pi over 3. Well, what is pi over 3? It might work better to convert that in degrees. It would be 60 degrees. Okay, so now we have, so the cosine of pi over 3, let's label these sides. This is a 36 and 90 right triangle. The cosine of this will be adjacent over hypotenuse, 1/2. That's the cosine of pi over 3. The sine of pi over 3, we're going to use the same triangle here. It's the opposite over the hypotenuse. So root 3 over 2. Cosine of pi over 2. This is confusing. We can't have a right triangle with one angle as a right angle. Other angle is a right angle. How does this work then? How can we make a triangle if they're both right angles? Well, let's think about what happens if we approach 90 degrees. Let's say we get really, really close to 90 degree angle. Kind of something like that, right? If we make a right triangle, it looks like this. This is really, really close to 90 degrees. If we get even closer, it might even look like this. So basically, it's really, really thin, right? We can assume that if we go to 90 degree angles, it gets infinitely thin. Okay, so when we get to 90 degrees, if you didn't know this already, this was 90 degrees. So the cosine is the adjacent over the hypotenuse. Well, if it's infinitely thin, this right triangle, kind of looks like this now. It's really, really thin, like a pencil. Okay? The adjacent is tiny, and the hypotenuse is huge. So if it's infinitely thin, it's a very small number over a very large number. So it would be 0. Cosine of pi over 2 is 0. Okay. What about the sine of pi over 2? Well, that's the adjacent over the hypotenuse. We can see that they're equal. Because it's literally just like almost like a pencil. So if they're equal, then it's 1. A number divided by itself is 1. So those are the values for cosine of pi over 2 and sine of pi over 2. 0 and 1. Cosine of 0. Well, now let's have a 0 degree angle here. It look really, really thin. This is the right angle. 0. So now it's thin in the opposite direction. The cosine is adjacent, which is this bottom part, over the hypotenuse. And they look exactly the same. They're basically the same number if we go up to 0. So 1. Sine of 0, opposite over hypotenuse, 0. Right? The opposite is very tiny, and the hypotenuse is very big. So that would be 0. So these are the definite values we have for sine and cosine for these angles. Now I'm going to move on to something really, really cool. So let's assume that SOHCAHTOA didn't work for you. Let's just say it didn't work, right? So another way to remember SOHCAHTOA, let's say we have A, B, and C here. This is our angle theta. We know that the sine of theta is B over C. We know that the cosine of theta is A over C. Right? Let's move the C to the other side. This is just a different form of SOHCAHTOA that may make it easier. C times the sine of theta equals B. C times the cosine of theta is A. Let me tell you why this is a little easier to remember. So let's say C is the hypotenuse, right? Right here. That means the leg here, so this is our angle here. The leg kind of like, if you think about this like an alligator, okay? The open jaw, the open mouth, that side length is C times the sine of theta. The bottom part of the jaw here is C times the cosine of theta. And I like to use this form a lot more. For me, this is a lot easier to remember. So C times the sine of theta is kind of like that open part, right? That open part. The angle looks like this. So C times the sine of theta, which is just B, is the open part. It's like the space between the jaws. And then A is the bottom jaw, which is C cosine theta. Okay, so cosine is the bottom part, and sine, c times sine of theta, is like the open part of the jaw. Okay, I hope that makes sense. That's another way you could consider sine and cosine. Now let's go to something we call the unit circle here. When I said unit circle, it's a radius of 1. So let's say we had a unit circle on the coordinate plane. And we had some angle here on the unit circle. What are the x and y coordinates of this point? Well, if we were to trace it down, this would be our x coordinate. And this would be our y coordinate, right? Remember what he said about the jaws and so the open part of the jaw, which is y, is 1 times the sine of theta. The bottom part of the jaw is 1 times cosine theta. We can get rid of the 1s. So the cool thing here is that if we have an angle on the unit circle, the y-coordinate of that point that it intersects with the unit circle, the y-coordinate is the sine of that angle. And the x-coordinate is the cosine of that angle. Okay? So if we look at the unit circle here, sine of 120 is root 3 over 2. That's what the unit circle tells us. Cosine of 315, that's the x-coordinate, root 2 over 2. So the x-coordinate kind of looks like that, okay? So this is what the unit circle tells us, and it's true. If we have a unit circle, which means radius 1, the x-coordinate of this point is the cosine of the angle. The y-coordinate of that point is the sine of that angle. It's the actual quantity. That's the definition, okay? Remember when I said there's a set value for what the sine of an angle is and the cosine of an angle? This is the set value, okay? Does that make sense? So take a screenshot of this unit circle. You can find unit circles all over the internet, but take a screenshot of this because it's here. And practice with it, right? So what I'm basically going to tell you here is to memorize these values. So memorize that the cosine and the sine of 4 pi over 3 is negative 1/2 and negative root 3 over 2. So I'm telling you to memorize these. Okay? These are the actual values. And if you have enough practice for these, you'll remember them really quickly. Okay, so take a screenshot. Let's do some really quick problems here to practice using our unit circle. Okay? Using the unit circle to find these values. This would be really quick. Just look at the unit circle and see what it tells you. Okay, so if you were to look at your unit circle, 150 kind of looks like this. It would tell you that this point has coordinates negative root 3 over 2, 1/2. And the x-coordinate is the cosine. What's that? Cosine of 150 is negative root 3 over 2. 210, if you were to look at this, it would tell you that this point is negative root 3 over 2, negative 1/2. The sine is the y-coordinate. So that's sine of 210 is negative 1/2. You can see that kind of looks like it. If you're to draw a 30, 60, 90 right triangle here, remember, this is 180. 210 is an extra 30 degrees more, right? So 30-degree right triangle, this is 1/2. So you can see that it is negative 1/2 as the y-coordinate. Okay. Tangent. Oh, remember the tangent is sine, cosine. So you got to find the sine of this angle and the cosine. It will tell you that the sine is -1. It will tell you that the cosine is 0. We can't divide by 0 though. Oh no, what do we do? Well, technically we can divide by 0. That's what they tell you in algebra. But yes, you can divide by 0 if you consider infinity. So if we divide some number by an infinitely small number, right? Imagine dividing a pie into sizes that are 0.00000 all the way down. Right? How many pieces would you have? A lot, right? If you were to divide a pie into tiny little pieces, you would have a lot of pieces. If you go all the way to 0, you get infinity pieces. So this is actually negative infinity. Your calculator will give you an error message because negative infinity, it doesn't know how to comprehend that. Okay, that's a tangent of 3/2. And finally, the cosine of 4 pi over 3, it's just going to tell you that the value is a negative 1/2. Okay, you can tell that I don't need a unit circle because I practice this a lot. So practice the unit circle. There's a lot of practice on the homework. And that's it. I'll see you guys next week.